Hello, everybody. It's super important in thermodynamics to be able to precisely define our systems, surroundings, and boundaries. It's crucial in order to understand all of thermodynamics. And we're going to dive deep into what those are, their meanings, the various types, and I got a cheat sheet list at the end that you can use for your course as well. So quite simply, the system is any three-dimensional region in space in which we wish to focus our attention. And the surroundings is literally the rest of the physical universe. And the boundary is some, say, three-dimensional surface that separates the system from the surroundings. Now, the system may expand or contract over time if the boundary may contract over time. And this boundary, it may be part of a physical surface. It may be real, such as the interface between two systems. So the interface between, say, a solid and a liquid phase, or a flask that's separating our solution from the rest of the lab or spilling on your lab partner. Or the boundary may be some imagined intangible surface that is not a real thing. It just might be some region in space that we say, over here is the system, and over here is the surroundings kind of thing. And if that boundary might be fluid, then the system may be fluid and change as well. Now, we often think of the system as the physical world that we can interact with indirectly. So us and the devices we control and everything else, that's part of the surroundings. The boundary is part of the surroundings as well. Now, we may separate the system into various subsystems. So, for example, this is a schematic of refrigeration, and we don't need to know what all of these parts mean. But if we think of a refrigerator as the system, but we may want to get deeper into that system and divide it up into subsystems. For example, the evaporator may be a system, the compressor may be a system, and the condenser may be a system as well. And we also might think of our subsystems and put them together to create like a super system and call it the system. For example, if we have solid ice, we may consider that a system. We may consider the liquid water as a system, but we may want to look at both phases as a whole and just simply call it the system. If the system is open, it can exchange matter with the surroundings. Mass can come and go. If it's closed, then it can't. But regardless of if it's open or closed, the system may exchange energy as heat or energy as work with the surroundings. It's going to depend on the boundary and the process. An isolated system cannot exchange matter or energy. So its mass and its total energy is constant over time. I have this Q here. Q means energy transferred as heat, and W stands for energy transferred as work. We also have another type of an open system called a control volume, where it has a set volume here, and matter can come in. We have a mass flow through an inlet, and we have matter coming out, mass flow through an outlet. So that's an example of an open system. But we still may be able to transfer energy as well. If we stir it, then we're transferring energy as work. And if we're heating it up, if we allow heat transfer, then we can get energy in or out of it as well. Okay, let's talk about boundaries. So this Coke bottle is an example of a closed system if we think of the drink. And I also like to think of the headspace and the liquid together as the system. And the plastic bottle and the lid is comprised of the boundary, and that boundary is also part of the surroundings. If our boundary allows heat transfer to go through, we call that a diathermal wall or a diathermal boundary. If the boundary does not allow heat transfer, so it's thermally insulated, then we call that an adiabatic wall, just like in a thermos. So a thermos will stay hot most of the day, pretty much all day. This is adiabatic. Now, in real life, nothing is exactly adiabatic. There will always be some heat transfer over time, but we can really thermally insulate it and make it solar shielded and whatnot to make it as adiabatic as possible. So if we look at adiabatic here, we allow no heat transfer, but it does allow work to be done on or by the system. So we can still transfer energy as work. And if it's diathermal, we allow heat transfer going through. And if it's diathermal but rigid, that means it can't expand or contract, then there's no pressure volume work that can be done. I've got lots of videos on what work is and whatnot. You can check those out if you like. So this system is essentially isolated if there's no other work allowed. We could maybe have electrical work or other types of work, however. Now, a boundary that is semi-permeable allows for matter to be exchanged with the surroundings. For example, if we have a semi-permeable membrane here, this allows the smaller yellow balls, the solvent molecules, to pass through the boundary, but not the larger solute molecules here. So this is an example of an open system. All right, so here's some cheat sheet lists that you can use. If the system is open, it allows for the exchange of matter, and it may allow for the exchange of energy as heat or work. We would need to know what the process is or more details. If it's closed, then that means no matter can be exchanged, but energy still could be exchanged as work or heat. And an isolated system cannot exchange matter or energy with the surroundings. So for boundaries, we think about energy being transferred as heat or being transferred as work. And if the boundary is diathermal and rigid, it allows for heat transfer because it's diathermal. If it's rigid, it can't expand or contract, so it doesn't allow for expansive or pressure volume work. But other work, like electrical work, may be permitted. If that diathermal wall is not rigid, then it can expand, so it allows for heat transfer and pressure volume work, and possibly other work as well, depending on the process. An adiabatic boundary does not allow for heat transfer because that's what adiabatic means. If it's rigid, it doesn't allow for pressure volume work because it can't expand or contract, but other work may be allowed if we have electrical work or anything like that, depending on the process. If that adiabatic wall is not rigid, it can expand or contract, then even though heat transfer is not permitted, it may allow for pressure volume work or other work depending on the process. Great, so there you have it. I've got many more videos on the fundamentals of thermodynamics that builds you up all the way to the more complicated concepts. Hang in there. I know thermo is not easy to learn, but you can survive. Cheers.